Algebra 1 Lesson 46, we are looking at our roots and not only our square roots but higher order roots. So a couple of vocabulary terms that we have for this lesson. Principal square root, we are looking for the positive square root of a number. Sometimes we like to say, oh, -9, or the square root of 9 is 3 or -3. Well, not really. When we're asking the square root of 9, we're really looking at that principal square root, which is just 3. Cube root, we are looking at a number multiplied by itself 3 times is a cube. So the opposite is a cube root. We're looking for something times itself 3 times, giving us our radicand. So when we look at our square roots, oftentimes we see this. We might just see the square root of x. But really what we're saying is that index is 2. Our square roots have an index of 2, and we might have an exponent on our x. Well, in this case, we can show our roots as a fractional exponent as well, where the exponent becomes the numerator, and the index, okay, that 2, that may or may not show up when we're talking about square roots. Okay, we might just see the square root, but it definitely comes up when we're talking about cube roots or fourth roots. These are indexes, okay? And that becomes the denominator of the fractional exponent. So let's try a couple. Or this is another way to talk about our higher order roots. If we have a to the n equals b, then the nth root of b is a, or the nth root of b, we can see it in equation form, is a. What we're saying is if we have a to the n equals b and we want to solve for a, we can take the nth root of each side, because taking something to a power and taking the root of something, those are opposite operations. So a is the same as the nth root of b. Okay? So, when we have something like the cube root of x, we see that the exponent on x is 1, so it goes in our numerator, divided by the index, which is 3. Let's try a few more of these. So let's say we have the nth root of x to the m. Well, with this, our exponent is m, so that goes in the numerator. The denominator is n because that is our index. The point here is to get to a place where we can start simplifying some of these. Some of them will be able to be simplified, but let's practice. In this case, we have x to the 3 over, well, since this is a square root, there's an imaginary 2 right there as our index, so 3 over 2. Our second one, x to the 2 over 3, x to the 4 over 3, and x to the 5 over 2. None of those fractions simplify nicely, okay, and we're not going to put them as, we're not going to say we have 1 and 1/3. We're not going to put them as mixed numbers, so we leave them as is. Okay, so let's try these. We would say we have x to the 8 over 4, which we can simplify that to 2. What we're saying here is, if I want the 4th root of x to the 8th, I want something multiplied by itself 4 times to give me x to the 8th. Well, x squared works, because x squared times x squared times x squared times x squared does give us x to the 8th. Second one, we have 6 over 2, which is x to the 3rd, and 6 over 3, which is x squared. So we can simplify some of these. Okay, keep going, and we can say we have x to the 10 over 5, or x squared, x to the 9 over 3, or x cubed, x to the 2 over 4, which is x to the 1/2, or we could say it as well as the square root of x. And lastly, x to the 4 over 2 is x squared. Okay? All right, now, if we start looking at some numbers, if I want the cube root of 64, what I'm saying is I want something times itself 3 times that will give me 64. Well, if you don't already know that 4 times 4 times 4 is 64, a way that I could get there is actually using prime factorization, which I could say, all right, 64 split up I could say, well, that's 2 and 32. Split it up more, 2 and 16. I could say 4 and 4, and I have 2 times 2 times 2 times 2. I have all of these 2's. I actually have the cube root of 2 to the, well, 1, 2, 3, 4, 5, 6th. Okay, which really is 2 to the 6 over 3, or 2 squared, which is 4. So prime factorization can help. The cube root of 125 is 5. Cube root of negative 8, we can actually do this. Unlike square roots, we can actually take the cube root of a negative number, and we see that negative 2 works. And for the last one, negative 10. Okay, how about with fourth roots? Fourth root of 81, well, something times itself 4 times, that's going to need to be 3, and you can prove that by prime factorization. Fourth root of 16 is 2. Fourth root of negative 1, that is impossible. It actually gives us imaginary numbers, so that's not going to work. And fourth root of a negative number is not going to work. Our even numbered roots, we cannot take negative numbers to an even numbered root. 216 to the 1/3. What this means is we are doing the cube root of 216. That is the same thing as 216 to the 1/3, which is 6. 343 to the 1/3 is 7. Negative 27 to 1/3 is negative 3. And negative 8 to the 1/3 is negative 2. You can prove all of those on your own. And lastly, some fourth roots. The fourth root of 10,000, well, 10 times 10 times 10 times 10 gives us 10,000, so we would get 10 here. 625 is 5. And if I'm taking the fourth root of a negative number, I cannot do that. All right. Let's just do 2 more examples, but some word problems this time. A gift box in the shape of a cube has a volume of 3,375 cubic inches. What is the side length? Well, a cube, if I'm finding the volume, I can say a cube is s cubed to get our volume, which is 3,375. Well, to solve this, sorry about that, not sure what's going on here. So, if I'm going to solve it for s, I'm going to take the cube root of this, which means I'm going to take the cube root of the other side. So s is equal to, well, you might know that it's going to be a bigger number, but not super big. It's actually going to be 15. And we could take and say 3,375 and do some prime factorization. Well, since it ends in 5, I would imagine that taking out a 5 would be a good idea. So 3,375 divided by 5 is 675. And that looks like another 5 can come out. So I get 135. And let's see, another 5 can come out. And I'm left with 27. And this 27, I can see that it actually splits into 3, 3, and 3. So I am left with the fact that I want the cube root of 5 cubed times 3 cubed. Or, since those exponents are the same, we could actually say this is the cube root of 15 cubed, which is 15. Now in our second one, we have a box that has 631 cubic inches less. So when we do that, we end up having 3,375 minus 631, which is 2,744, equaling our s cubed. So when we take the cube root, we are going to say s is equal to, and you can go through the prime factorization, ends up with 2 cubed times 7 cubed, which means that we have 14 as our side length. Well, I hope this is helpful for your homework and for studying.